Okay, well, I first want to thank the organizer for inviting me. I would have loved to come in person, but unfortunately I had to stay in the cold in Paris. So let me start. Okay, the talk is about the paper you see on the screen, which was published a year and a half ago. And it was a collaborative work with Carlos Cartes, who's in Chile, Enrique Tirapegui, who was in Chile, but unfortunately, sadly passed away in 2020, and Rahul Pandit from Bangalore. So let me, before I start, just say a few words about Enrique. Enrique was my first mentor. I started working with him as a student at the end of the 70s. And at the time, we were studying systems with noise. And in the framework of non-equilibrium physics, we did some work on the Schlegel model of autocatalytical chemical reactions. So it's a paper from the end of the 70s. Okay, so here is an outline of my presentation. I will first start by the system, the physical motivations for the work, and then I'll give the system definitions, trying to make things very clear and explicit about the details of spectral truncations and conserved quantities for the truncated burgers, and about what are the stationary probabilities of the both forced and unforced system. Then I will turn to numerical results. I will first say a few words about the algorithms that have been used to do the computation and the main physical parameters I choose to vary. And then I will give the main results, which are one on the scaling of the correlation times, and two on the distribution of the interface increments. And then I will give a short conclusion. Okay, so about the physical motivations. The inviscid-Burgers equation in 1D, when it is spectrally truncated in Fourier representation, is perhaps the simplest system one can think of, having absolute equilibrium, that is stationary probability, with, because it's a 1D system, an equilibrium spectrum, which scales as a constant in K. It turns out it's been known for some time that if you look at the correlations of the temporal fluctuations of the truncated Burgers dynamics on the equilibrium or around the equilibrium, they have a correlation time that scales as the wave number to the power -1. Let me mention that this K-1 scaling is also found around different types of absolute equilibrium in 2D and 3D with the truncated Euler, truncated MHD, and also truncated Gross-Pitayevsky dynamics. So it's very general to have this K-1 temporal scaling. One remark in 2 points. In D dimension, the absolute equilibrium E of K scales as K to the D-1, but there is still a K-1 scaling for the correlation times in 2 and 3D. And thus, tau of K cannot be simply related to an eddy turnover term time that you would build from the energy spectrum, because then it would depend on dimension. All right. Okay, some remarks about the K-1 scaling. It's the same scaling as the so-called sweeping effect. This is because if you want to make things dimensional, you have to multiply K-1 by a velocity. So when you have sweeping, it will be the sweeping velocity. And this is kind of strange because it's only dimensional, what I said. And the idea of sweeping is that you have a large scale velocity that sweeps everything. But here in the absolute equilibrium, the large scales do not dominate the energy spectrum. Okay, now more about the subject of the talk. When you add dissipation and noise to the 1D truncated inviscid Burger systems, it morphs or turns into the famous 1D KPZ equation that is well known in statistical physics. Okay, and in this framework, when there is a standard renormalization group field theory or otherwise argument that gives you the k-3½ scaling for the KPZ case and k-2 scaling for the so-called Edward-Wilkinson case, which is when the viscous term dominates. But there is no trace in this computation of a k-1 scaling. Okay, I gave some references here. These are the first classical papers on renormalization group applied to hydrodynamic system from the 70s, end of the 70s. Then the famous KPZ paper, and a couple of more recent papers, 2003, 2015, because there has been a revival in the study of the KPZ system, big revival recently. About this revival, some mathematical motivations. Martin Heyer had the field medal 2014 for his mathematical work on the KPZ equation. So this problem does also interest mathematicians. All right, let me jump to be more precise and to the system dissipation. So we will consider the randomly forced generalized 1D Burgers equation. So why generalized? Because I added a forcing term like this, which is the derivative of a space derivative of a white noise in space and time. And it's generalized because Burgers equation would be with lambda equal 1, and to keep in line with the standard KPZ notations, I put a lambda in front of the nonlinear term. Okay, so up to integration constants, in fact, the KPZ system is more written like this. So you can get this one by taking a derivative of this one, or if you want up to an integration constant, the so-called interface height, because the KPZ equation is really an equation for H, and H describes an interface, a growing interface, okay? And then this is the standard system, so maybe they have a minus sign here, I don't know. But anyway, this is the standard equation in the KPZ system. And in what will follow, so I will consider this system in 3 cases. So the first case is the one I talked about up to now, the deterministic inviscid 1D truncated Burgers. So this is lambda equal 1, nu equals 0, and d equals 0. So then we have the inviscid truncated Burgers. Then, of course, there is an Edward-Wilkinson, which is a linear problem you can completely solve, which is this problem when lambda equals 0. And then more generally, there is the KPZ equation when all 3 parameters are non-zero, okay? A note of caution. A lot of literature on the subject is on the 1D Burgers equation with different correlated forcing noise. Let me go back. That is not with this particular space derivative of a noise white in time and space. In many other studies, they study different type of noise, because with this noise, as we will see in what comes, it's only with this noise, the derivative of the white noise, that the truncated Burgers equation admits the same equilibrium. So I will not study these problems, and I will concentrate on the only non-trivial thing, which is the time correlation, because when you put this noise, the equilibrium is trivial in the sense that you can find it analytically. Okay, so to give you an idea about how the system looks, these are runs I did with Mathematica on a laptop. So what you see is the velocity as function of space and time. Here as a movie and here as an XT plot. So the darkness is proportional to velocity, and this one is the Edward-Wilkinson regime, the linear one. This one is in the KPZ regime, and this one is in the inviscid, okay? So there is nothing much to say, except you can notice that there is no difference between right and left in Edward-Wilkinson's, but in KPZ and inviscid, the dark region that is negative velocity go to the left, and the clear region that is positive velocity tend to go to the right. But apart from that, it's difficult to say more by looking at this low resolution laptop result. Okay, so now about spectral truncation and conserved quantities. So in general, we will always consider the 2 pi periodic boundary conditions in X, so we can fully expand the inviscid-Burgers equation. And when you do that, you get this equation in Fourier space, okay? So no truncations yet. And this equation, it's easy to check that it conserves the total energy. So not only the total energy, but integrating by part the nonlinear term, you can show that this infinite series of integral are conserved by the inviscid dynamics. And the energy is the case, special case n equal 2. Okay, so what happens when we apply a Galerkin truncation to the system? So what do we mean by applying a Galerkin truncation? It means that we introduce the Galerkin projector, which in spectral space puts to 0. This is the Heaviside function, which is 0 for all negative arguments. So as soon as modulus of k is larger than k max, this is 0, and the field in spectral space is put to 0. Okay, and the Galerkin truncation, it amounts in the spectral relation to replace u by the projected of u dxu by the projected of u dxu, and the noise also by the projector of the noise. Okay, so what happens when you do the spectral truncation to the Galerkin, to the conserved quantities? Okay, the Galerkin truncation version of the full equation, that is the untruncated equation, it reads like this because of the various projector coming in. You have projectors here. Thus, the nonlinear truncated term, you can write it explicitly like this with the 3 Heaviside functions, okay? Then, when you do this, it's straightforward by simple algebra calculus to check that the nonlinear term verifies, the truncated nonlinear term verifies these 3 relations, boom, boom, and boom. And this means that 3 conservation laws survive the Galerkin truncation. That is, this quantity, and these quantities. So they are respectively the momentum and the energy of the system, and the third surviving quantity, which is a cubic quantity, it can be used, it's been used by Maida, among others, Andrew Maida, to provide an explicit Hamiltonian formulation of the truncated systems. It is known to play a role in the thermalization dynamics only for a very special choice of the initial conditions, okay? Now, the stationary probability. First thing to notice is that the nonlinear truncated term verifies the Liouville property. So this means the following relation. It's got in phase space a 0 divergence. So if we think for a moment of absolute equilibrium, then the system, because of energy conservation, admits the microcanonical here distribution. When you have a large number of degrees of freedom, that is when K max is large, this can be in some sense approximated by the canonical distribution here. And these results also follow directly from energy conservation, because then you can show that the Liouville equation, which is the equation obeyed by the probability, it looks like this. So that this canonical thing is a stationary probability. Now, just a word about what is this canonical thing, exponential to the E divided by the temperature. Remember that E is the energy, it's U squared, it's quadratic. So it's a white noise in space at a given time. This is a white noise in space for U. So for the interface height, h of x, it's a Brownian process. So this stationary probability, the interface is a Brownian. Now, what happens, all I said up to now about the stationary probability was for the truncated inviscid Burgers case. What happens in Edward Wilkinson and KPZ case? So in both cases, you can derive, of course, a Fokker-Planck equation, which looks like this. So if you forget about this term coming from the viscosity, about this term coming from the forcing, there is a k-square here because we have an x derivative, remember, in the Burger forcing. So if you forget this term and this term, you just get the Liouville equation, and this is the Fokker-Planck equation with forcing and dissipation. So this stationary is also a solution of the Fokker-Planck equation, and this is because provided this relation, fluctuation dissipation relation, is satisfied, that is, there is a relation between the noise and the viscosity which is related to the equilibrium temperature, then it's easy to check that these two terms alone generate this, and that this is also zero because of the Liouville equation. So we are in a case, provided we take the forcing and dissipation according to fluctuation dissipation relation here, we always have the same stationary distribution. So that's why I said from the beginning that the only problem is the time correlation, because in this problem, the equilibrium distribution is always the same. So, okay, a few words about the numerical algorithms. We use a standard Fourier pseudospectral with de-aliasing performed by the two-third rule. Clearly, such a pseudospectral method gives the same result as Galerkin method. And there is an interesting detail I will mention here, is that if you de-aliase by the two-third rule, then the nonlinear term should be computed like this. Now, if you insist into computing the nonlinear term like this, I don't know, I have a window that hides, with just PG of U3, sorry, to evaluate, not the nonlinear term. The nonlinear term must be evaluated as the truncate. I'm talking about the third conserved quantity. So if you evaluate it like this, it will work. But if you want to evaluate it simply like this, then you need to perform the truncation for at Kmax equal n/4. And that's what my dad did in most of his computation. But what we do is put the computation at two-thirds and compute when we needed this quantity like that. The equations, the dynamical equations are the same, of course, because the nonlinearity is quadratic. So this is enough to remove, to de-alias the nonlinear term. Okay. No. Okay, so as I said, standard pseudospectral. The time step is the fourth-order Runge-Kutta method. That is for the absolute equilibrium case, because you need to conserve things very well. When the viscosity and the noise are weak, that is not in the Edward Wilkinson case, what we do is we advance first the system by the same, by this RK scheme, including viscosity in it. And then we add independently at the end the white noise as an extra explicit step. For large viscosity, there is a standard well-known implicit method that we use instead, because this would necessitate ridiculously small time steps. Okay, the time average of the correlation function is computed over the same interval for all wave numbers. Typically, we do a run for a few large-scale correlation times. The code is embarrassingly parallel. That is, we have a number of independent realization with independent realization of the Gaussian initial condition and Gaussian white noise. And the resulting independent time average correlation functions are average over the realizations also. Okay, now, the physical parameters. This is becoming to be more physical. Because we are working in a 2D periodic thing, we cannot touch the largest less scales, which is always 2 pi. So the thing we can vary is the smallest scale, which is resolution dependent and related to the largest wave number K max, which is the same order as the collocation mesh size. Thus, a given computation is parameterized by URMS, that is, what is the total energy, Kmax, what is the resolution of the truncated wave number, and nu, because D is fixed by the fluctuation dissipation relation, D is fixed such that the absolute equilibrium corresponds to URMS, okay? And of course, when nu equals 0, the URMS comes only through the initial data. And this is the fluctuation dissipation relation that fixes the value of the diffusion, the noise intensity. Okay, and that's it. Now, what are the physical parameters? When we do the nu equals 0 and D equals 0 case, we just integrate the inviscid-truncated Burgers equation starting from absolute equilibrium initial condition. And when nu is non-zero, it's the full KPZ system with lambda equal 1 that is integrated, also starting from the equilibrium distribution. Thus, in the KPZ case, one accepts to recover KPZ scaling of the correlation time. However, of course, in the large scales, of course. However, the speed of this approach will depend on the value of the parameter at small scale. So there is a scale-dependent Reynolds number that we can introduce in this problem as URMS over nu K. And when we evaluate this, so you see the Reynolds number, the Reynolds number is decreasing with K. And when we estimate this Reynolds number at the highest wave number, truncation wave number, it is minimum, that's why we call it R min, and it's just URMS over nu K max, or if you want like this. And so, in fact, everything depends on this number. And what you expect is that when this number is much smaller than 1, you should see Edward-Wilkinson scaling. When this number goes to infinity, you should recover the inviscid-truncated scaling. So we should get, something should happen when we vary the two, because in between we should get KPZ scaling. So that's how it works. Let me take some time to explain the plots that don't look at the blue-white thing, which is just noise. So what you see here are level of the correlation function, time correlation function, normalized at time equals 0. So the time goes like this, and the wave number goes like this, okay? And this is in log coordinates. So scaling would be a straight line, okay? Those are the lines of constant correlation function. And the little red dots you see on the line that corresponds to 1/2, because the levels are from 0, 0, 1, 0, 2, 0, 3, 0, 4, 0, 5. So the little red dots you see here are obtained independently by computing the wave number at which the correlation is half of its initial value, which is 1, okay? And you see that indeed this is just a check, they fall on the contour line. So this is the inviscid case, and this is a KPZ case. And so here you have K minus 1, here you have K minus 2/3. And if we look at a case with a larger viscosity, excuse me, this is the Edward-Wilkinson scaling, where here you have a slope of -2. So, okay, so I'm going to discuss more detail the crossover. So this crossover is, again, the correlation, the time at which the correlation is 1/2, what we call tau 1/2, as a function of K in log, okay? The different symbols or plots corresponds to runs with different value of nu, okay? And so this is with a large nu, and so we get Edward-Wilkinson. Then we decrease nu, and then we get KPZ. And if we further decrease nu, you see here we get K minus 1. So I have a better plot than that to discuss it. It's the same plot as the one on the right, but compensated by the power law for KPZ scaling. This is what you have here. And now also to be more physically motivated, instead of giving you the value of nu, I give you the value of the Reynolds number, minimum Reynolds number, that is the Reynolds number at the maximum wave number. So you have the numbers here. So you can see, for instance, these Edward-Wilkinson things. So you can see, for instance, the largest viscosity one, it does a good bit of Edward-Wilkinson, and then it goes away. It wants to go to the infrared fixed point, to the KPZ infrared fixed point, but here it's linear thing, so it gets a linear thing. And you get these things for R mean equal 0.12. And these things here are 0.12, 0.24, 0.48, and 0.98. You see, and here you just go to the KPZ fixed point, and boom, you do this, okay? And now, if you want to go on the other thing, if you take an R mean, which is 2 now, almost 2, you see that you start above the unstable Edward-Wilkinson fixed point, but you still recover KPZ. This is what you expect from a normalization group analysis, and so forth when I increase the Reynolds number. And I have to increase it a lot. And when I get, you see, when I get to 124, I get this. Let's see, 124, 63, 124, 63. This is 31. So it's only for 15 that with this limited range, I still reach the KPZ, KPZ fixed point. But for the other things, especially when it's infinite, boom, I stay on the K minus 1 thing. All right. Now, what about this K minus 1 inviscid correlation time? So it turns out that it can be understood very well analytically, that there is for short times a parabola with this time scale. It's a simple computation based on using the equation of motion, and you get, so you define this decorrelation time like this, and then using the equation of motion, this is the thing you want to compute, but each dt here, because of the equation of motion, is a quadratic thing in V. So you have two quadratic things in V. So this is a fourth order term. It makes a Feynman loop. You can compute it by standard perturbation theory arguments. And you find that this correlation times scales like 1/k. And here, okay, here is another of the results. I have to explain that a little bit. On the left, it's the KPZ thing. And on the right, it's the inviscid thing. So let's start with the simple on the right, inviscid. This is the correlation time. So it's obtained by rescaling the wave number. So instead of plotting, I plot here gamma of K, correlation of KT divided by correlation of K0. And here I plot KT for different K and different T. And because of this inviscid scaling, they fall on the same curve. And what I show here is the theoretical parabola. And this is the inset is a blow up of the parabola at short time. And so you see that for short times, it's this inviscid scaling is well resolved. Now, the left one is the same thing, the same idea as before. That is the correlation function, rescale correlation function for various wave numbers and time, rescaled using the KPZ scaling, which is KT to the 2/3. Okay, there is a number here to make the curve fit to what? To the black curve. And black curve is coming from, I think it's a Spohn paper, where it was computed semi-analytically. I mean, they had determinants on a special model, and they got this black curve, which the inset here is around 6. So it's between 4 and 6 is around here. That it's difficult to see here, but the curves goes a little bit negative. And you see that this is just to say that at this resolution and with this number of realization, when we think we are in the KPZ regime, our result reproduces very well the full scaling correlation function, including this little dip here. So we do believe that our system works in the KPZ regime the way we did. Now, I have some further results on the distribution of the interface increments. So, I mean, it's a complicated business. The motivation here is to show that we do have a system that truly follows all the prediction of KPZ when it is in the KPZ regime. So there is a known distribution laws, okay, according to recent theories. And so what we did is we check for, so this is the distribution of the interface increments at different times, etc. And this is the kurtosis and the skewness of this distribution plotted as function of times. So for short times, it starts with Gaussian initial data. So kurtosis and skewness, because it's they are completely off the grid, and then they seem to reach some asymptotic values. So when okay. So when you take the truncation scale Reynolds number of 0.98, which is the one that seems to be the closest to get pure KPZ, and if you use very high resolution 2048 runs, so as I said, for very small R-means, it should go to Gaussian, and for larger R-mean, it should converge to the theoretical value as long as our mean remains of order unity. A note of caution, skewness and kurtosis are known to converge very slowly with resolution in these problems. So here is the results. So you have a bunch of different R-means. So when they are too small, it's too little, and when they are too big, it's too large. But it seems it seems, can you all still see my screen? Yes? Hello? Because I got a message saying the participant can now see your screen. So hopefully you were able to see it. I guess someone would have protested. Okay. So I go on. So, okay, provided one starts at reasonable values, one is not too far away from the theoretical value, and I can now reach my conclusions. So, so as I said, the 1D truncated inviscid Burgers equation is perhaps the simplest system in which absolute equilibrium with energy spectrum E of k scaling as k0 can be obtained. The temporal fluctuation, they are k minus 1. When you add dissipation and noise, the 1D truncated inviscid Burgers turns into the 1D KPZ equation that is well known in statistical physics. However, that's main question and motivation coming from this work. It is in a renormalization group, only 2 fixed points are known: the Edward Wilkinson unstable and the KPZ stable. So, how could we describe in statistical physics terms the crossover to a k minus 1? So there are known perturbative RG, only 2 fixed points. So Leonid Khanin, who I see is on by Zoom also, told me some time ago that she had preliminary results that suggest the presence of a 3rd fixed point. Because I can have couple of minutes more, I guess. In this framework, let me try to sound sort of crazy idea before I finish. So the crazy idea is the following, and I'd like to ask the audience what they think about it, and maybe we can have some discussion about that. So let me go back to the original system. Okay, I see. Are you still listening to me? Can someone?
We see the.
You see? Okay, okay, it's working. Yeah, I was kind of.
Where was you?
Okay. You are still with me. So, okay, there is. I have not tried it, but I'm thinking of doing it. So I give you the new crazy idea now. There is yet another way to modify this system, keeping the basic thing we have here, which is that when we take both nu and d to 0, we have inviscid, and when we have nu and d non-zero, we have KPZ. So, but both have the same equilibrium, okay? So the idea is the following. I don't know if you guys have followed that, but there has been a few papers recently about the fractionary Burgers equation. That is, you take the Burgers equation, and instead of a Laplacian here, you put a power of minus Laplacian to the alpha over 2. So for alpha equal 1, it's the standard Burgers equation. For alpha larger than 1, this is the so-called hyperviscous Burgers equation that was considered by a number of people, including Sam Reddy and Uriel in this room. And the point is that some recent things have shown that you can take alpha down and including to 1/2. And when alpha is 1/2, that is when you replace the k square by absolute value of k here, you can still show mathematically that there are no singularity. But this is the limit point. If alpha is less than 1/2, you do have singularity, okay? There are some results like that, more or less recent. So my crazy idea on which I would like to induce, if possible, some feedback from the audience is the following question. Have you heard, has anybody ever considered, let's say, the equivalent of the KPZ system, but instead of having a K square, instead of having a K square here and a K here, you put K to the 2 alpha here and a K to the alpha here, and you take alpha, you play with the value of alpha. Why do I do this? Because the limit case, the lowest case that I can go to, at least for the full Burgers equation without singularity, is alpha equal 1/2. And when you look at the scaling, so the equivalent of the Edward Wilkinson case, instead of scaling as K to the -2, it will scale as K to the -2 alpha. So if we put alpha equal 1/2, we get that the linear part will scale exactly like the inviscid. So I go back to my conclusions. No, will be faster like that. Come on. I would rather go like this. Okay, so going back to these things, I have a question for the audience and Leonie Khanin. Is it possible in the perturbative renormalization group to consider this system with an alpha different from 1, so alpha going from 1/2 to 1? And also a question for Leonie, is it possible to do this in the framework of the non-perturbative functional renormalization group? And question, could that in any way help with the mystery about is there somewhere in the renormalization group a fixed point associated to the inviscid infinite Reynolds number scaling? Thank you.
Thank you very much. Let's thank our speaker. We have time for a few questions. I see that Rahul is one to ask.
You asked for a comment about models where you would get a mod K instead of K squared. I think such models have been looked at by the flame front people in the Kuramoto-Sivashinsky context. I mean, normal Kuramoto-Sivashinsky is K squared and K to the 4. But people have looked at models with a mod K. Okay, but those are deterministic models, they're not stochastic. But, you know, we all believe that Kuramoto-Sivashinsky long distance, long time behaviors are like KPZ. So that's one thing you could look at. Okay, thank you, Rahul.
Thank you. I see a few questions from the Zoom participants. So let's go alphabetically. Brachet, your question.
Yes, about your remark, Marc, we are presently running log lattice simulation. You know what are the log lattice? These are the technique invented by Alexei Khmelybaev and Ciro Campolina. And we have been recently running Burgers equation with hypo and hyper dissipation, and but we didn't do the scaling of the forcing as you suggest. So, but we have interesting result, and we study the singularity strip, etc. We have blow ups and things like this. So, if you are interested, we can discuss with you about this.
Okay, thank you.
But it's very interesting. So it's not real DNS because you know, it's like a shell model, but a little bit more elaborate. But it can give interesting clue for your question.
Okay, All right, thank you.
Yeah.
Leonie Khanin.
Yes.
Okay,
So
fine.
hello, Marc, and thank you for the very nice talk. So regarding your question, so as it was said in the room, indeed there is Kuramoto-Shibasinski, where you change the power of the Laplacian, and it has also been studied, of course, if you change the power of the forcing of the noise. And here it's known that if you exceed some values, then it leads to another fixed point, which is a long-range KPZ fixed point. So you end up in another universality class. And here it would be the same. I mean, if your power leads to non-analytic dependence, then you will switch to another universality class. Yeah.
Sorry, is this perturbative or functional RG?
Both, actually. Both.
Okay.
So it was done for in what concerns the noise. It was done in the very early paper by Medina and collaborators.
Okay,
but to get the k-1 scaling, I think you don't need any of this. Really, this fixed point is here. It just has been overlooked so far in KPZ. But it's clear that it's here. As I told you already, and it's quite simple to understand, because in KPZ you really have just one constant, which is this G, which is a combination lambda squared D over nu cube. And in fact, the limit you're looking at, the inviscid limit, is really equivalent to the infinite lambda limit. And so on, if you draw the line as a function of this G, somewhere in the middle at finite G, you have the KPZ fixed point, which is attractive. On the one hand, going to G equals 0, you have Edward Wilkinson. But if you go to the other side, then you have the G infinity fixed point. And it's your inviscid Burgers limit. So unfortunately, we had to stop working on that for a year, but I really hope we will resume soon, and I can give you what is the value and what is the scaling function as this infinite G fixed point. And I'm quite sure it will match your results. But okay, this is work in progress, and I hope to tell you more soon.
Okay, thank you very much.
Yeah, my personal view is, and I don't know, it can be discussed. In any turbulent system, the way the energy is produced and then how it is dissipated, that depends on the force or the strain fields present. Depending on whether one type of strain field as here, I mean, thermal gradients or pressure gradients or magnetic forces or whatever be the strain fields and our force fields present. It depends on the cascade, the energy, how the energy cascades down or dissipated, depends on that. And so the crossover points and the number of scales produced, it also depends on that. So it's a complex thing. But anyway, in a any turbulent system, if we have to understand what is the dominant physics. So it depends on whether fluid physics is dominant or some other physics is dominant.
Oh,
so that's my general.
I'm sorry, it's not a question, and we can.
Yeah, you can discuss on this.
We are talking about this talk.
Yeah.
Somebody wants to ask anything else? Well, I want to make a remark. Marc, there is a approach to connect between KPZ fixed point. Connection. So it's called intermediate disorder. Basically, it means that if you scale the constant in front, coupling constant in front of your forcing, scale it with time, like 1/t in power 1/4.
I don't hear you anymore.
So if you scale the coupling
hear
constant like 1/t in power 1/4, but t is the time, then you had intermediate disorder which connects between Edward Wilkinson and KPZ. So That's described in our papers with Jeremy Costel and Tom Alberts in Phys-Rev Letters, almost 10 years ago, 8 years ago. So there is a connection, and there is kind of one parameter family of kind of fixed point, a curve which connects Wilkinson fixed point with KPZ fixed point. So you can look at that. It's just, but then you need to scale the forcing proportion, like 1 over time in power 1 over force. But you can look at it. By the way.
Okay, thank you.
Okay.
When you talked about the coupling constant, I mean, coupling between physics and you assume some.
It's just a coefficient. It's just a coefficient in front of the forcing. Thank you very much, Marc. It was very clear and very nice talk. And we have a break now for